Okay, so let's get started with lecture number 11. As you know by now, lecture number 10, our university was snowed out on Tuesday and it closed, so I posted the video from 2022, and someone asked, why didn't you post the video from last year? Why did you post the 2022? And it was because in 2023, I was at a conference for that lecture. So I had posted the same lecture from 2022, and so I haven't given that lecture in almost 2 years, which is kind of funny. But it's good that we have a good video for that lecture, and nothing has really changed about Minimax and alpha beta in the last 60 years or so. So the algorithm is still the same. As you can see, so we're here today on Thursday, and next Thursday is the midterm exam. And so by Tuesday, when I explain assignment 3, I am trying to get a better room for you to write the exam in than this one, because writing exams on those little, whatever you'd call those, is going to be really difficult, at least in my opinion. So on Tuesday, I will announce the room that the exam is going to be in. If you don't hear anything, then it's just in this room. Okay, so if there's no post on D2L by Tuesday, then it's just in this room. And so the exam, I'm going to make a D2L post about the exam, what you can expect to find on it. But basically, if it's in the slides or it's in an assignment up to the exam, so that includes up to and including assignment 3, that's the content that's on the exam. So it's pretty easy. If it's in the slides, then it can be a question. If it's not, then it can't be a question. Okay, so today last time we talked about the Minimax algorithm. Today we're going to talk about enhancements that you can make for the Minimax algorithm, because assignment 3 is all about Minimax. So let's get into that. So lecture number 11, Minimax search enhancements. These algorithms have literally been around since like the 1950s, 1960s. And in the 60 or 70 years since then, people have made sort of gradual improvements to these algorithms. Not the algorithms themselves, but little things that you can do on top of these algorithms that help the eventual strength of a game-playing agent that you would want to make with these things. And of course, I cannot possibly cover 60 years of research in this area, nor would I want you to necessarily know all of that or expect you to implement it on an assignment. But what I'm going to do is cover some of the stuff that you could do in assignment 3, and some stuff that I don't expect you to do in assignment 3 and may not actually be possible in JavaScript, but are nevertheless interesting things to learn about in the field. And just before I get started, so there's some useful links here for the topics in this lecture. The first two are the chess programming wiki. And the chess programming wiki is one of the best resources on the internet for heuristic search, especially two-player game search. And so I've included 2 links to the main page there and the recommended reading section. That's what they recommend. If you're super into like assignment 3 and you want to know like more about how to make game-playing agents stronger without going to something like deep learning or reinforcement learning, then I recommend having a look at that. There's really, really excellent lectures there. The next 2 links are by a YouTube channel called Coding Adventure. And these are not going to be on the exam. Now, when I say if it appears on the slide, it can appear on exam, that doesn't mean that every YouTube video is there. If I link a YouTube video, and I will later in the course, and I say this is going to be on the exam, right? I will definitely tell you if a YouTube video is going to be on the exam. But I highly recommend watching these 2 videos because A, they're super interesting. They are the most Coding Adventure. Has anyone ever watched any of their YouTube channels videos before? I guarantee once you watch one of these, you'll be subscribed. It is the highest quality programming videos that I've ever seen, and I wish that I could make videos as high quality as these. Unfortunately, I give about 28 hours of lectures every term, and I'm sure that him making one of his like 40-minute videos probably takes weeks of editing and stuff like that. But it's amazing. It's really incredible. And once you start, what I would probably recommend is start assignment 3, or don't start assignment 3 and just watch the first and second of those videos. Especially the second one, it's beautifully done. And it shows the way in which a lot of these suggested techniques for improving the power of your search, like, okay, I started out and I was winning 53% of my games, and I implemented this thing, and now I'm winning 58% of my games. And he goes through implementing like 15 different things, and by the end he's winning like 95% of his games, right? So it's a really excellent video. Right here, this video is interesting because it's kind of the story of how, so Dr. Jonathan Schaefer is a computer science researcher from the University of Alberta, and he solved checkers. So checkers is solved, like algorithmically solved. Every possible position on a checkers board has been enumerated and recorded. And that journey of going from, you know, having a decent, like your assignment 3 version of a checkers playing agent all the way to beating the world's best human, that is Jonathan Schaefer's talk on how that journey happened. So later on in the course, we're going to be watching the movie AlphaGo, which is Google DeepMind's journey in creating AlphaGo. That is basically the AlphaGo of checkers. It's not an actual movie, because it's just Jonathan Schaefer giving a talk. But a few years ago, he actually visited our department. I worked with him a bit when I was at the University of Alberta. He's an excellent speaker, very entertaining, really smart person, one of the grandfathers of heuristic search, in my opinion. So if you're interested in that sort of thing, I would also recommend watching that. But of course, that content is not going to be on the exam. So before we get started, I want to say a little note here about actions and moves. Because depending on the resource or the game or the environment or the particular person who's telling you something or the lecture video that you're watching or the wiki that you're reading, you may see the term action or the term move used in a game setting. And so essentially, action and move are basically interchangeable. Okay, so if you go to the chess programming wiki, you'll see a move. Now, a move does not necessarily mean that an agent has moved a physical location. It essentially just means an action. Okay, so action and move are usually used interchangeably. The only time I've seen them not or have a tangible difference is in some games when you have, like, let's say you have an alternating turn game where I take a turn, then you take a turn. I take a turn, you take a turn. Sometimes in those games, one turn can either be called a turn or a move, but sometimes those moves or turns consists of many individual actions, right? So for example, you might roll a dice and then read a card and then move one piece and then move another piece and then that's your turn. Okay? In that case, I have seen move be used to mean a sequence of actions. Usually action is an atomic action, just doing one specific thing, and a move could be for a turn. But this is all kind of overkill terminology. I just didn't want you to be like wondering when you were reading the chess programming wiki, what is the difference between a move and an action? But for our lectures, an action is essentially a move. And so at some point in the slides, you may see action. At some point, you may see move, and that just depended on, you know, whatever came out of my brain at that time and put into the slide. Another thing that's very important is just a little note on state evaluation, because this is going to be very important for assignment 3. So as you do the Minimax search, as you saw in the last recorded lecture, hopefully, eventually you come to a point where you need to actually evaluate the state. You give it some score, right? And so down here at the bottom, at these evaluation nodes, the reason you would evaluate a state is usually one of two reasons. One is that that is actually a terminal state of the game, like you're in checkmate, or you have no pieces left on the checkerboard, right? Or the game is over, essentially. So someone has won, someone has lost, or you've both drawn, or something like that. That is one reason for you to apply an evaluation, when the game is actually over. Another reason is that you've hit some sort of computational limit that you've set for yourself. So you saw that we had iterative deepening alpha beta in that lecture. And so what happens is, just like iterative deepening depth first search, we go to a certain depth, then we go to the next depth, then we go to the next depth, then we go to the next depth. And part of that is doing that sort of depth-limited search where you say, okay, I'm at a given state, or I'm at a given node in the search, I'm down in the search tree, I'm at a given depth. I have to check if that depth is greater than or equal to the current depth that I have set for my limit. And if I have, then I have to return an evaluation for this node because I've gone as far as I can. And so these are non-exact evaluations. So what I mean by an exact evaluation is a win or a loss is like -1 or minus infinity for a loss, plus infinity for a win, or some big number or something like that. Usually we go with -1 to +1, something like that. That's an exact evaluation. It's as bad as possible to lose. It's as good as possible to win. And typically, it's completely neutral if you draw. But for a depth limit, we don't know exactly how good this state is because we've just stopped the computation. It could happen that at depth +1, we lost the game, right? Sometimes, for example, in chess, we may take the queen piece and be really happy with ourselves, but then, that was all just a ploy by the other player to sacrifice the queen to put us in checkmate. So we can never be sure of the exact evaluation of a state unless we've reached a terminal node. And so that's just a quick note on that. And to go further, the heuristic evaluation or the heuristic function or score or value of a state, it can be a little bit confusing because of that at first. And so the maximizing player wants to take the highest value, and the minimizing player wants to take the lowest value. And the reason for this is, and so because of that, the score should always be calculated with respect to the maximizing player, right? So you look at a board, or you look at a game state, and you're trying to evaluate that. You are always evaluating the board with respect to the person who's maximizing, the person who is to act at the root node of that search. That's sometimes a little bit confusing. And so because of that, you want to keep track of the maximizing player somewhere in your search, right? Because you might be at depth 7, and then you're like, oh crap, who was the first person to move again? Well, you want to be able to look that up somehow. And so typically, when you have a state evaluation, the maximum possible good thing for you is the maximum possible bad thing for the other player, right? So if it's +1 for a win for you, then it should be a -1 for a loss for the other player. So in assignment 3, and I'm not getting to the details of assignment 3 yet, we'll go over that ad nauseum in the next lecture, but what you'll see is we will have an evaluation function like this. And that evaluation function will take in 2 parameters. It will take in the state, and it will take in the player. And essentially it says, okay, let's see who the winner of this game is. So I'll give you the function for whoever has won, and the result of get winner, look at a state and see who has won, is going to be one of 4 possible things. You may say, okay, that's weird. How are there 4 possible outcomes to a game? Well, what I've done down here is I've created these integers, and they're just named player 1, player 2, player none, and player draw. So those are the 4 possible outcomes for a game. And here it says, if the winner is the player that we passed in, then return some really big positive number, right? That is the best possible evaluation for the state for this player because they have won the game. Otherwise, if the winner is, and look, if player 1 is 0 and player 2 is 1, then in order to alternate back and forth between one player and the other player, we add 1, mod it by 2. So it goes 0, 1, 0, 1, 0, 1. So this says, if the winner is the other player, return negative, that big number. Now, it doesn't have to be 10,000. It could be, whatever you want. If the winner is a draw, that means in the game for our Connect 4, which we're playing in assignment 3, it means that the whole board is full and no one has won. Then you return a 0. Otherwise, if nobody has won and there's no draw, it means that the game is still ongoing. And so nobody has won the game yet. Therefore, return some heuristic evaluation of the state, right? And remember, this non-terminal heuristic evaluation in a game like chess, you might have a function that's like, okay, I'm going to add up all the pieces that I have and add up all the pieces that you have and do some subtraction or something, some guess at who's winning, right? And if you then call this, so inside our alpha, beta, or minimax function, we have this line here, which is saying if the winner is not equal to player none, this says if the game, so player none means the game is still ongoing. So if the game has stopped, meaning that there is a winner or a draw, or the depth is greater than the maximum current depth, that's when I evaluate the state with respect to the maximizing player. Okay, so we have to say if the state is either terminal, meaning that the game is over, or we've reached our depth limit, that's when we do this evaluation. So those are just some quick notes on evaluation to try and clear up things before the assignment so that you know that. Okay, and hopefully this will help clear up also some of the enhancements that we're going to talk about in this lecture. So there are two main types of enhancements that exist in computer science, essentially. One is like implementation efficiency enhancements. So these enhancements will speed up the implementation. So if you have to do something 1,000 times or 1,000,000 times, and you can do that 1,000,000 things in half the time, that means you can typically search more things. And if you can search more things, meaning you can look further into the future with Minimax, then that usually means a stronger AI, right? But this will not affect algorithmically like the number of nodes that we search up to a given depth, right? So for example, when we had Minimax and we added the enhancement of alpha beta, if we search to depth 10 with Minimax, if we search to depth 10 with alpha beta, we're cutting like the vast majority of those nodes by applying alpha beta. But these implementation efficiency enhancements do not cut the number of nodes to a given depth. They don't like theoretically change the outcome. They just speed things up. And then there are search enhancements, which typically are either improvements to the heuristic evaluation function somehow, or techniques for guiding the search tree, right? Or pruning off nodes and stuff like that, which will actually possibly cut nodes off of the search. And so these can result in fewer nodes searched to a given depth, and if you have to search fewer nodes, then you can search deeper, which means typically you'll do better. So in one of those videos that I just showed by Coding Adventure, this is what he does. So he starts out with version 1, like this sort of vanilla version of alpha beta that he coded for chess. And then, so he plays version 1 against itself. And you might say, why am I interested in playing it against myself? It's just going to be 50-50, probably. And so you can see here that that's approximately true. So he had, out of 1,000 games, 347 wins, 298 draws, and 355 losses. So approximately the same number of wins as losses, but you're also going to see a number of draws, right? So then he implements this enhancement, and this one, and this one, and this one, and all sorts of enhancements up until the very end, where he's winning 90% of the games and drawing 7% of the games and only losing 2% of the games, right? So none of these, like once you get beyond alpha beta, like alpha beta is a huge improvement over Minimax. It's absolutely gigantic, and you'll see a huge jump in playing strength when you do that. But all of these things I'm about to show you, neither one of them is going to turn your like amateur player into a grandmaster player. But putting them all in can make really significant improvements over the playing strength of your bot. But just realize that neither one of them alone is going to like make the thing be way better. So let's get into some of these things. The first one, and I kind of go in order of typically the most problematic for the assignment, up onto like, okay, you're probably not going to implement this, but it's interesting. So the first thing I see is people come to me and they say, why did my bot do this really stupid move on turn 8 or whatever? And if your program is not broken, it can still make really stupid moves sometimes. And why is that? Well, sometimes your program is looking far into the future, 10, 15, 20 moves if you've programmed it really good. And what it sees is, okay, no matter what I do, I'm just in such a good position, I'm going to win. Or no matter what I do, I'm in such a bad position, I'm going to lose. And so what happens is, in these cases, it might make stupid moves until it gets to the win or the loss, because it sees no difference in the value of the states until then, right? So the bot is kind of thinking, well, I'm going to win or lose anyway, so who cares what I do until I lose? But here's the thing. Even if you have figured out that you're going to lose, that's under the assumption that your opponent is as smart as you. So there's no point to give up because maybe they didn't see that path that you saw, right? So if you're searching to depth 20 and you see that you're going to lose, and the opponent is only searching to depth 10, well, they may not have seen that yet. So if you just have this like defeatist, well, I'm going to lose anyway, I might as well just make a random move. And the reason for that is because the scores, all the evaluations are all negative 10,000. So the bot isn't like, it's obviously not, it doesn't, we're anthropomorphizing here by saying it thinks this way, it has a defeatist attitude or whatever, but it literally doesn't see any difference between any of the moves because they all lead to failure. However, how can we do something where even though the outcome is going to be the same, we don't want to make those stupid intermediate moves? Well, that's where sort of tie-breaking comes in and what I've been alluding to here. So let's differentiate between wins and losses. And I said, okay, a win is a win and a loss is a loss. Yes, but wouldn't we prefer to win as soon as possible? And so in this class, what I do is for assignment 3, you submit your AIs, and then I actually run a tournament between like all the players that you submit. And so it's like remarkably exciting when it gets down to like the last few players. And what you'll see is sometimes in Connect 4, your object of the game is to put 4 pieces in a row of your color, right? Sometimes there'll be 3 in a row, and it's your turn, and all you've got to do is put a piece there. Like picture you're playing X's and O's, and it's like XX blank, and then your AI just doesn't put it there. And it looks like your AI is just like showboating and like trying to show off or whatever. But this is the reason, right? And it's because you haven't differentiated between taking the win right now or winning 10 terms from now. But you would prefer to win as soon as possible, and you would prefer to lose as late as possible, right? Now, in terms of like human versus human games, if you're playing chess like professionally or in a tournament or whatever, and you kind of know that you're going to lose, like there's no chance, people will kind of get annoyed at you if you don't resign, right? Like why play it out for another half an hour when I'm already going to lose? So sometimes, in human situations, it doesn't make sense to do this, but you would prefer to lose as late as possible, if possible. So what we're going to do is we're going to tie break a win or a loss by incorporating the turn number of the game. So in Connect 4, like whatever game state you're programming, whatever game you're programming, you can just record, this is turn 12, this is turn 30, this is turn 31, whatever. In Connect 4, it's really easy because you just count up the number of pieces on the board, so that's the turn number. And so if we take the win value minus the turn number, then what we will prefer are faster wins, right? Because let's say our win value is 1,000, and we're on turn 40, so that's 960. But if we were going to win on turn 50, that's 950, right? So this formula lets us have a higher value for winning sooner by subtracting the turn number. And it's just the opposite for losing. If we add the turn number, then we prefer longer games when we're losing, okay? So I highly recommend that this is something that you do in your assignment, because if not, you definitely will, like this is not a bug of it taking poor moves, it will do that. If it can't differentiate, it will just take essentially random moves or however you choose to tie break. And so I recommend tie breaking like this. The next really interesting thing, which isn't super noticeable, and it's kind of controversial, this one, and it depends completely on the game. Okay? And sometimes it will have absolutely no effect. Sometimes it may have a big effect. And so it's not provably good or bad to recognize this, but I think it's interesting to talk about. So what do I mean by tree depth parity? So if you treat the root node as depth 0, right, sometimes you might treat the root node as depth 1. Sometimes you might treat it as 0, depending on how you've implemented it. If you treat it as depth 1, you just flip the parity. It's the same rules apply. So if the root node depth 0, then on the even depths of the search tree, the maximizing player is moving, right? So on depth 0, maximizing, 1, minimizing, 2, maximizing, 3, minimizing. And so it alternates between maximizing and minimizing. And alternatively, or oppositely, On the odd ones, the minimizing player is happening. So, evaluations on even and odd depths intuitively mean something different, which is really interesting. Because on the even depths, these are optimistic evaluations, right? For example, maybe I just captured your queen, and then I evaluate the state immediately. But what I'm doing there is I'm not factoring in your next move. And if you've ever played chess, I'm sure you can realize that there's a lot of bad things that you can happen after you capture their queen. Maybe you're checkmated. Usually they're just going to take your queen right back. It's very unlikely that you just get a free queen, right? So if you think of evaluating right after an even node, then this is a hugely optimistic view of the state of the game, right? And if you think about it, if all you do is look to the point of pure optimism, that may not be the best way of actually evaluating your state, okay? On the opposite hand, if you evaluate to odd, then your opponent has moved last, and so you are evaluating the board after your opponent's move. And so this is a pessimistic view, which theoretically may be better in some environments, because if you're doing the best possible thing you can in response to the worst possible thing that could happen, that's typically a better move than just hoping that this good thing that I did doesn't get retaliated against. Okay? So there's something to think about there, and it can have interesting effects on the evaluation. So for example, what some people do is instead of going, depth 1, depth 2, depth 3, depth 4, they'll go 1, 3, 5, 7, or 0, 2, 4, like whether or not you want optimistic or pessimistic evaluations. Again, nothing super mathematical that I can say about that here, or I can't prove anything, but you can see how that may intuitively have an effect. This is an interesting one because it can dramatically affect the running speed of your program. So this is one of those implementation efficiency things which will not theoretically affect the performance, but it may speed up your program like a lot, depending on the environment that you're working in. So, I meant to have this appear one at a time. That's okay. So to build a search tree, we issue actions to the current state to create a child, right? So we're at a current depth, and then we create a child, and we go to that next depth. The child state is then passed to the next minimax depth. So there's two issues with this. Typically, when we create objects in programming languages, like JavaScript in this course, those are passed by reference, right? So it's passed by reference. So if I change a state, so the first one here, first issue, if I loop through the actions of a state, I'm going to say something like, okay, I have some pseudocode in another slide. So the first issue, and I'll explain it then, when I loop through an action, the state is changed. So if I loop through action 1 and do an action, and then I loop to the next action and do the action again, well, in the same loop, I've modified the same state twice. So I've said do this action and then do another action. When in actual fact, when I'm looping through that second action, I want to do it to the original state, not to the state that's been modified by the first action, right? So there, that's an issue, right? Maybe I would want to copy the original state or keep a copy of it around and then have that copy issue the action in order to make sure that I'm not changing it. And in pass-by-value languages, it means that the current state will be modified when the child states are modified if it's not copied. And so the solution to this is just to copy the state when we look at a child or when we create a child. And so here, sort of a visualization of this. Oh, why did that turn into gray? That's interesting. So up here, if we have this current state, and then we look at what happens if this action is issued. So we take this state, we issue the action, and now we've got a different state. And then in that for loop, if I then apply this action, well, I'm actually applying it to this state, right? So every time I loop over the actions, I would have to say, take the state that I'm currently at, copy it, then issue the action. And then for this one, copy that one, then issue the action. Copy it again, then issue the action, right? So every time I create a new child, I have to copy the state. And if your state is large, that copy can be very expensive. Copying a chessboard, copying a video game state. Now, in a case of Connect 4, which, there's like 42 integers or something like that, it's not that big, but copying those arrays, copying those vectors is a very slow operation. It's way slower than looking at the data and performing some, calculation on the data. So if we look at the Minimax function and the alpha beta function, we've got this part down here where we're saying for each of the children for each of the children C of state S, we are going to be passing it into the next recursion call of alpha beta, right? And so if we how do we get C in children S? Well, this has to be copying somehow in order to do that. So let's have a look at that. If we didn't copy, here's the code that we would have. For every legal action A, do the action at the state and then pass it down. And like I said before, if this state is not copied, like it isn't here, right? Now, okay, one could argue that you could have the state itself, when we say do action, return a copied version of itself or something like that. But we're not doing it here. We're modifying this state. And then we pass it in. Then by the time we get to the next iteration, we are now modifying the modified state, which will completely break, right? But not only that, what we are doing is then passing this state down through Minimax, and then the next depth of Minimax is also modifying that state. And so we modify it all the way down, and then when it comes back up, we are now actually looking at the version, like when I come back up here to do this action, well, I might be looking at the version of the state that was modified down here somewhere, right? Because I've passed it by reference, I've passed it by reference, so therefore all the modifications that I've made are done. So the solution to this is to copy the state, right? Every time we want to make a child, we say child equals state.copy. Now this has to be a deep copy. Hopefully you've all heard of shallow copy versus deep copy. Because, for example, a shallow copy, if there are pointers or arrays or something, may just copy the references to those arrays, but you're actually still modifying the same array. So when you copy the state, you have to make new arrays, fill it with the same stuff, and then return it. That's a deep copy. Then we do the action to that child that is now a copy of the state, and then we pass that down, and this solves all of our problems. But, as you can see by the title of these slides, how could we possibly avoid the copying? So, this is what I'm calling the undo action optimization. Copying can be very, very slow, depending on the size of the environment. Do we really need to copy? Sometimes, yes. Sometimes, no. And that completely depends on the environment that we're using. If it is possible to undo an action in our state, then we don't have to copy. So how does this change our code? Let's have a look. Look at this. If I have all the legal actions, I do the action. Oh, sorry, this is supposed to say state, not child here. So let me modify that real quick. Okay, so here, I got to get my thing back up. I do the action. I pass it down into the next depth of Minimax. Then, when it gets it, it's going to be getting that new state. It's going to do the action. It's going to get passed down. Then the next blah, 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 until I get to a terminal state, it's evaluated. Then the recursion starts unrolling. And as soon as this finishes, I undo the action. And now, the state is back to the state it was when I started the loop. And so this way, if we have an efficient way of undoing an action, then what we can do is just do the action, then make the Minimax call, then undo the action, and this will work. And it will be tens of times faster, probably, per node than copying it. Now, depending on the programming language, etc. But keep in mind, that is not always possible to undo an action. So for example, if you capture a piece in checkers, or in chess, right? You might say, okay, just keep track of the last move that I did, keep track of where all the pieces were. Well, that's just as bad as copying the state, right? In some games, or if there's some randomness, maybe you didn't record what the randomness was, etc. This will be possible in assignment 3. So we're playing a game called Connect 4. The pieces always stay on the board. There's no captures. And what I can do here is, for example, if I just place this piece here, what happens in Connect 4 is I choose a column, I place a piece, it goes down until it hits another piece. So I have just placed this piece here. And so if this is do action 0, 1, 2, 3, 4, so this would be action 4. If I've just done action 4, in order to undo action 4, all I have to do is remove the top piece from column 4. That's it. And so Connect 4 is one of the games where undoing an action is the easiest. Okay. Another thing is move ordering. And again, what I recommend for assignment 3 is just to get 100% on the assignment, and then if you want to start trying to implement some of these things, then you can do it, right? So just do copying at first, then do then go back and try and make it more efficient. Whenever you see a link like this in the title, that goes to the Chess Programming Wiki page for that topic. So there's a move ordering topic on Chess Programming Wiki. So if you're looking at the PDF, you can just click that link. So with Minimax, all actions are considered, with Minimax, okay, one second. My brain is frying here for a second. So with Minimax, we consider all of the actions at all of the states to generate the children, right? We look at every single possible action. With alpha beta pruning, not all of the actions are checked, right? There are some of them. If we have a current alpha beta window and a state falls outside of that, we can prune that action. And so with Minimax, if we have to check all of the actions anyway, then the actions could be in any random order. It doesn't really matter, right? Because we have to check them all. But in alpha beta, it does kind of matter what order the actions are in. And it turns out that if the better actions, meaning either the more positive actions for me or the more negative actions for the other player, then the alpha beta window will narrow faster and we will actually get more cuts in alpha beta. So ordering the actions with a heuristic evaluation can potentially lead to more cuts. I've heard somewhere that it's like the square root in the best case, but I'm not sure if that's true. So I'm going to remove that because I shouldn't say things that aren't true. Or I'm not going to say things that I don't know for sure are true. But this can yield a dramatic improvement in playing strength. But there's no guarantee. It depends on the environment, and you have to sort of do this experimentally. So what you could do is you could say, give me the legal actions for a state, and then you could have another function that sorts those actions, and then you can run your bot against itself with the sorting and without the sorting, and see which is better. That's typically how we do it. Okay, so that's a pretty simple explanation. Another thing is called search extensions. Search extensions, again, that's a link to the Chess Programming Wiki, is that Minimax looks equally deep for all of the actions, right? But if you're a human player looking at a chessboard, if you've ever played chess, what's a stupid move that you could do right off the bat? Move one of the pawns on the very edge of the board up. You're not going to sit there and look at okay, what happens after I make one of the worst moves possible, right? And look 20 moves deep there. But Minimax looks equally deep for all the good moves and all the bad moves. So something that's possible is that it might be in our interest to look deeper for actions with interesting outcomes. So if something interesting has happened, for example, if I have an action which leads to a check, maybe I say, for that action, look one depth deeper, or however much depth deeper, because it may be more important to look there than the action where I just lost a piece or something like that, right? Or in Connect 4, maybe if someone has a 3 in a row or a 2 in a row, maybe I could look one depth deeper. Maybe that would be advantageous. And again, it's not guaranteed. It's just something that could impact it. In chess, it definitely does impact it. I've never tried it for Connect 4. Maybe it would. Okay, now I'm going to talk about something that if you're programming in a real language, not JavaScript, is possible. I don't know how possible this is in JavaScript, and I do not necessarily recommend doing any of this or trying to do it for our particular assignment, but I do think it's super interesting, and I have done it for games, and it was like a very worthwhile endeavor and feels really cool when you when you get it done. So we'll eventually talk about bit boards, but in order to talk about bit boards, we have to talk about bit operations first, because not everyone is super familiar with bit operations. So in lower level languages like C, I think you can do bit operations in JavaScript. I'm not 100% sure. Don't shoot the messenger if I'm wrong about that. So we can directly work with every bit of information that we have in memory, right? Bit operations are extremely fast. One of the reasons why is because they're parallelized, right? All the bits of a particular integer are done at the same time. They can be used to perform many intuitive and useful functions. So, an integer is either a 32-bit or a 64-bit value based on your operating system and the bitness of your operating system. And so we can manipulate integers with bit operations. So what are bit operations? Bitwise AND is a bit operation. So say we have this integer up here. These are just random numbers. I just typed in ones and zeros. If we bitwise AND this with another one, that does AND individually in parallel with all the bits in that integer. So if they're both 1, it's a 1. Otherwise, it's a 0. That's what bitwise AND does. It does it for all the bits in that integer. Bitwise OR just does it with OR. So if either one of them are 1, then the outcome is a 1. Bitwise XOR, that is exclusive OR, meaning that if the two bits are different, it's a 1. If they're the same, then it's a 0. Okay, so those are the standard bit operations. There's also, do I have this? Oh yeah, so there's left shift and right shift. So if I have the bits right here and I bit shift left by 3, this literally takes all the bits and moves them to the left by 3. And if it goes off the edge, they just get truncated. Okay. Similarly, with a right shift here, so you can see how we have 1 0 1 1 1 and then 2 zeros. If we shift this right by 3, then the last one will be chopped off. Okay, so that's bit shift right. And then we have a bit negation, and this just takes the opposite, right? So this is a unary operator where we have no other, it's not a binary operator, it just has it operates on an integer. So we take all the bits of that integer and we negate it. Okay. What can we do with those? Well, there's something called a bit set. Has anyone ever used a bit set for something before? Oh, I love me a bit set. Okay. One of the most common uses for working with bits is the concept of a bit set. And so bit sets are sets of bits of length n. So if you have a 32-bit int, you can use that to represent a set of 32 things, right? And there's to the n possible combinations of things that you can store in that set. So for example, we have a 16-bit integer here, which would be a short in C, and that has 16 things that we could store in it. So each element of the bit set is typically represents a Boolean true or false associated with the index of that set. And I'll have an example of that later. But we can think, okay, I'll have an example of that in a bit. So here's an example. We have a set of integers. So say my set of integers is 1, 4, 6, 7, 8, 12, 14. Whatever that means. Maybe I'm literally just storing integers. Maybe these are like options for my program or a configuration. Maybe this is the game state of a board, right? I can represent that as a bit set, where I have bit 1 set to 1, but there's no 0 here, so 0 is not there. So we count the bits and we set them to 1, so we have 4, 6, 7, 8, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, but not 15. Okay? So we've taken those integers and we've stored them in a bit set. Now the obvious disadvantage of this is that we could not store integers that are longer than our integer could handle, right? So that's, you can only store however many things that's in your 64-bit int or 16-bit integer, for example. But if we have something like the options for the configuration of a program, typically we don't have more than 64 options for our program, so a bit set could be an efficient use of that. So that would be a 2-byte short in C, and usually we have a 4-byte or a 4-byte integer or an 8-byte long, and so there is no overhead in going from this short to an int. Typically, in modern 64-bit programming language, using a short would be converted to a 4 or 8-byte integer anyway. So just use the 8-byte one if you can. So here are some bit set operations. So typically when you're using bit sets, you want to have some defined values, which may be useful to you, right? So this is the right one being set. So however big our integer is over here, this R1 is just the value where I have the rightmost one set to 1, everything else being set to 0. This is the L1, and in whatever size of bits, this may be how that is represented. So you have 1, 0, 0, 0. So that's the left one. So if you want to have a set containing a single 1 in bit n, so let's say we want the third bit set to a 1, then we could have the L bit, right? So L bit, do I have an example of this? I don't have an example drawn. But take the L bit, which is 1, 0, 0, 0, and then if I shift that to the right by n, now that is in the nth place. So if you're asking, okay, how do I set the individual bits, you can use these values with a combination of bit shifting to put it into the right place. And also, if you want to test to see if there is a 1 inside bit n, then what you can do is you can take that value that you're trying to compare against, which is, and then you're trying to see, okay, so for example, this may be number 00010, so it's in the second place. So if this is 2, right here, we say s bitwise and with a bit at position n. So we can test to see if that bit set, let me go back to an example here where I have a big number. Okay, so if I want to test if this value is a 1 in this bit set of many possibly different things, what I would do is have a number which is all zeros, except this is a 1, and then I do bitwise and if I do bitwise and with that, if it has a 1 in that place, the answer will have a 1 in it. And if it doesn't have a 1 in that place, then the answer will be 0. So now if I check to see if it's 0, then it doesn't have the number. If it does have it, then it does have it. So that's what that operation is. And so basically what we want to do is we have a set of things. We want to be able to put things into it and check if things are in it already, and also remove things from it. So this is the start of that. If we want to do the intersection or union of two sets, now this is where the power of bit sets starts to really appear, is that in parallel, in a single operation, I can take the intersection of two sets by bitwise anding them. I can take the union of two sets by bitwise ORing them. Super fast, right? If I want to add or remove from a set, if I want to add a set to another set or an individual item to a set, I OR equals it. So I say it equals this or that thing, and ORing it adds it to the set. And if I want to remove it from a set, then I AND equal with the negation of it. And that's how I remove it from the set. And then, so what I can do here is I can just create little functions or define macros if I'm using something like C for add bit, remove bit, toggle bit, check bit, all kinds of things. And so I can just have these functions here that do that for me. Also, if you want to iterate through bits, here's how you do this. You're not going to have to do this on the assignment, so I'm not going to spend too much more time on that because I got to get through the rest of it. But it's essentially, and also what you may have seen in other programming languages is you'll have something like int options equals option 1 or option 2. For example, in lots of graphics libraries, you'll have display options which are like full screen or vsync or no title. And what that is doing is, for example, if option 1, which might be full screen, they'll have that as a 1 in the first bit or the last bit. Option 2 is a 1 in the second bit. Option 3 is a 1 in the third bit. And if we OR them together, now we have our bit set of all the options. So if you've ever seen something like this in a programming language, you're asking, why are they ORing things together? It's because they're using a bit set to store all those options. So it's a very fast, efficient way of storing a set of options. Now, let's drill a little bit more down into the XOR operator. The XOR operator, again, just says if they're different, it's a 1. If they're the same, it's a 0. Okay, XOR operator has a number of different cool properties. Look at this. So this is A XOR B, that's equal to C. A XOR 0. Well, this is all zeros, so all the 1s are going to stay 1s, and all the zeros are going to stay zeros. So anything XOR 0 is itself. And similarly, anything XOR itself is 0. Now, that's a very interesting property. Okay, so A XOR B is just B, because A XOR A is 0. And this is transitive. Okay, so if it was A XOR B XOR A, you can just say if there's an even number of A's, I can just remove them all, right? And so more properties down here. Again, it's transitive, so A XOR B equals C means that C XOR A is B and C XOR B is A. And it's reversible as well, which is very important. Here's a really cool thing that I like to show about XOR. Let's say that we have a bunch of data that we are very concerned with. Okay? So this is theoretically, in a very hand-wavy way, how something like a RAID array works, a RAID array of hard drives. So let's say we have 4 disks, or any number of disks, n disks of data that's very important. And we want to make a system such that if any individual disk dies, we don't lose our data. Okay, so we want a system where one disk can die and we don't lose our data. So you may say to yourself, okay, that's pretty easy. Just duplicate the whole thing. And then if any disk dies, we've got a backup of it. Okay, but that's doubling the cost of your data, right? So if I've got 4 disks, now I need to buy an additional 4 disks. What if I made something called an XOR disk? Now, XOR is often called a parity operator because XOR, if there's an even number of 1s, it'll be a 0. If there's an odd number of 1s, it'll be a 1. That's an interesting way of looking at the XOR operator. So what we can do, no matter how many disks we have here, we do the XOR of all of these. So let's say that somehow hard drives are magically sorted into columns like this, which they're not, but just think of bit 1, bit 2, bit 3, whatever. For each of those bits on each disk, we store the XOR of all of those. Okay? So we store the XOR over there in that last disk. And we can do that for no matter how many disks that we have, as long as we have more than one. Now let's say that that disk dies, and we lose all the data on that disk. Well, what did I say about XOR? It's reversible, right? So let's plug a new disk into the system, and this value is going to be the XOR of all the other disks. And look, the XOR disk is now the same contents of that original disk. So no matter how many disks we have, we can ensure that one disk can die without loss by adding a single other parity disk. Now, I said this is sort of how RAID works. There are many different RAIDs. They don't work like that. This is just a theoretical way of thinking about it, where you could say, how could I possibly back up 10 disks with just one disk? Right? Now, if 2 disks die, you're screwed. Right? You cannot recover both operators, but you can recover one of them. So I think that's a really cool example of just how powerful XOR is. So now that we've done that, I do not recommend this for assignment 3, but I thought it was super interesting, so I'll talk about it, and that is bit boards. So many board games are stored on 8x8 grids, right? Chess is 8x8, checkers is 8x8, lots of games are 8x8. That just happens to be 64. Isn't that a really convenient number for computers, right? Now, this doesn't mean that boards that are smaller or bigger can't use bit boards. It just means that this is super convenient. Bit boards can be used to store the positions of sets of pieces on the board. So in C, I can use a 64-bit long int to store a bit board. And this will allow us to do many AI-related tasks in parallel. So let's just have a look at that. If I think about it, how would I normally, what's the intuitive, naive way of storing a chessboard? Well, what I would do is I would probably, because I like working with integers, I would have an integer associated with every piece, right? Maybe I have a data structure or a struct or an object called a piece, and that would be it would have the color and it would have the type. So I might have a white rook or a black queen, right? And so I would make an array of size 64 or 8x8 of those piece objects, and then on the board I would either have I would have a piece where there's nothing there, or I would have a piece where there's something there, and so I would store that. So whatever your data structure size is, for storing a piece, it would be that times 64. That's how much memory you would need. However, you can think of a chessboard as a bit set. Now you might say, okay, but a bit set is only ones or zeros, so I can't store different pieces in a bit set. I can only store something like maybe if there is a piece there. So what they do is they create a bit set for every possible piece, right? And it turns out that the memory usage for every possible piece having its own integer is still way less than 64 times the data structure for an individual piece. So for example, here's the bit set storing the locations of the white pawns on the board at the start of the game. That's the bit set for that. Here is where the black rooks are, or the black castles on a board. And what we do is we have one bit set for every possible piece color combination that's in the game. And then our bit board is basically a stack of all of these things. Not a stack as in, first out, but like a physical pile of those, right? So we have a bunch of them. So over here, these would be the black pawns. These would be the white pawns. This would be the white bishops, the white knights, the white rooks, the white queen, the white king, and the opposite for the black pieces. Okay, so we have 1, 2, 3, 4, 5, 6, 12 bit boards, right? Because there's 6 different types of pieces, 2 different colors, 12 integers storing the board instead of 64 times the integer that we would have by naively just storing everything in an array. And then we have the rank and file, etc. And you may say, oh, that's cool, but all it does is save us a bit of memory. Oh no, you can get so clever with this, it's crazy. So let's say I want to know all the occupied squares on the board. Well, here we go. I take the white pieces, OR them with the black pieces, that's the union, and now I have the occupied squares for the board. Let's say I have a bit board, so my queen is here, right? I have a bit mask. Well, so a bit mask is essentially just a bit set that I'm going to use for a specific type of operation. So I have a bit mask associated with where queens can attack from that square. And if I take the intersection of where my queen can attack and the pieces where my opponent's pieces are, now I can have in one operation all of the possible pieces that my queen can attack on the board. I don't have to iterate through going diagonal, 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 going down, 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 checking this array. I can do some operations in parallel on the entire bit board. Negation. Why might I care about negation? Well, the opposite of the occupied squares are the empty squares, right? So now I can do things like this. If I want to move a piece up, down, left, or right, then if I'm at 0 and I've got a single 64-bit integer as a bit set, then if I want to go up, well, that's 8 bits to the left. If I want to go down, that's 8 bits to the right, or vice versa. 7 for northwest, 9 for northeast. So all these calculations take some time. Like, you may not fully get this right now, but if you ever try to implement a bit set, it's really cool. There are things that you need to do, like population count. There are many different bits in a set. I want to know, for example, okay, I've got a bit set of all the opponent's pawns, and I want to know how many of them there are. Do I need to check all 64 possible bits? So population counting is one of the slower operations on bit sets, but there's many optimized ways to do it. Some modern hardware has a thing called pop count. Pop count will just tell you how many ones are set in a bit set. You can iterate over them in interesting ways. So there's population count, there's bit sets, bit boards. All those are on the chess programming wiki. I recommend looking at them. So many people have worked on chess-specific operations for bit boards. Like, is a piece attacking a square? Is a given side attacking a square, etc.? Lots of cool things that you can do with bit boards. And the optimized functions are way faster than like looking up something in an array, iterating over the different pieces in the board, etc. So I just wanted to mention that. I don't necessarily recommend doing something like that for the assignment, but I think it's really cool. The next really interesting thing, and I sort of mentioned this before in the class, but not in any detail, are called transposition tables. So if I look at this chessboard, how many different ways are there for me to get to this particular state, right? So this state, yes, it's a single state of the game. But what I'm doing in search is I'm searching sequences of actions. So I might run across this state a bunch of times in a search, right? Because if I look here, I know this is kind of hard to see due to the color. Apologies for that. So for example, if I only consider these knights, well, I could have moved this one first and this one second. So if I think about my search tree, I'm going down to the left and then down to the right. But if I went down to the right and down to the left, I end up at the same state, but I'm at a different place in the search tree, right? So the search tree can be a little bit misleading, and we talked about this before when we talked about state space versus game tree complexity, and how the number of possible states there are in a game is far, far fewer than the number of possible ways to reach those states, right? So transpositions are interesting. So in a given search tree, we may come across the same state many, many times. And the causes for transpositions, there are two main causes for transpositions. One of them is that there are many ways to get to the same state, as we just said. The game progression may naturally be able to get us to the same state in multiple different ways. However, even if there's a game in which you cannot get to the same state in many different ways, we are still doing iterative deepening alpha beta. So if you think, if I've got an iterative deepening alpha beta and I'm going from depth 1 to depth 10, well, I'm going to see all the states at depth 1 at least 10 times. And the states at depth 4, I'm going to see at least 6 times, right? So these duplicate states are called transpositions, and they're either caused by one of these two reasons. So it may be advantageous to store information about those states as we encounter them in the search tree. So for example, maybe I store the heuristic value, right? Maybe I store the best move or the best action that I calculated the last time that I was here. Maybe I store the search depth that I found those things at. Maybe I store a flag for those things. So for example, is that score an exact score, right? Was that like a terminal state when I saw that? If it was, I can just stop the search right now, right? So for example, if I see a particular state and I know that Minimax says that that state with optimal play leads to me losing, the next time I encounter that state in my iterative deepening alpha beta, why would I bother searching down that path again, right? I already know it's a loss, so I'm not going to gain any information, so it's just a loss. Return it. Save myself exponential time by searching it. Other information, etc. So the idea here is that you use the table to store information about a state that we've seen before to use when we encounter it again. Do we know the exact value of a state from a previous search? Then we can stop the state and return the value. And also we can do things with, okay, when we reached that state before, it was an alpha beta cut. It was an alpha cut at this particular depth. So we could say something like, okay, if I'm doing a search that's now shallower than that other search than we did, then I know that that search that we did before is actually going to have more information about that state than I could possibly get from this search. So look at that logic and say, okay, I can use that value instead of searching it again. And just a little example here. I know this is really hard to see in class, but this is from a German paper that I found, so I couldn't find one in English. But this is a Sonder transposition table, which means without transposition table, and this is met transposition table. And so this over here, this is the depth of the search. And so this searched for, I think it was, they gave it a 3-minute time limit. And because, depth is exponential, the search time for a next depth is going to be exponential with respect to the previous depth. And so look at this. Without a transposition table, we searched 282,000 nodes, and we got to depth 13 in 163 seconds. But with a transposition table, we did that same search in 4 seconds, and we only searched 5,000 nodes, right? And down here, with the transposition table, we were able to search in the same amount of time to depth 27, right? Now, this doesn't mean that your program necessarily goes from like amateur to grandmaster, but a transposition table is one of the best possible improvements that you can make to a search algorithm, right? And it can save you exponential time, as you can see, like really exponential time saved 98% of the computation time. And the reason for that is, as you go deeper and deeper in the search, you're seeing the same states more and more. So the deeper you go, the more the transposition table actually matters. So I am not requiring the transposition table be implemented for assignment 3. That would be an insane amount of work. Maybe if this course was all about heuristic search, we could take a week to implement a transposition table. But I really wanted to mention them because they're really cool. And I think if nobody in the class implemented a transposition table for assignment 3, and one group did, they would instantly win the competition. Like, that's how strong it is. Maybe I'll have bonus marks if you do it. So the complete details of the transposition table are out of scope for the course, but here's an important thing. In order to store that data, how am I going to store it, right? So in order to store the data, we need to be able to associate a game state with an index in the table. If we could somehow hash the game state to the table index, then we could store the data, right? Think about a data structure. How do I store this chess state, or this Connect 4 game state? How do I turn that into a lookup address into something? Well, we've talked about hashing, but now we're going to talk about the coolest hashing I've ever seen, which is called Zobrist hashing. So we often want to store information about particular game board configurations. And so what we need to do is say, okay, my table, whether that's a transposition table, you could also have a heuristic lookup table. So for example, if your heuristic function is really, really good, but it's really slow to compute, then instead of having a full transposition table, you could have a hash table that just stores the result of your heuristic function, right? That's a really easy one to do. But we do need to have some sort of integer associated with that board. And so we need a hash function which can turn a given game state into an integer, which can be very, very difficult. And so one method for doing that is called Zobrist hashing. Zobrist hashing is going to make use of two big tools. One is a big table of random numbers. Random numbers are nice for some things. And then a bitwise XOR operator. And so the first thing we're going to do is we're going to, one time at the start of our program, we're going to create this big table. And the big table says, for every player, for every possible piece that they could have, and for every possible piece that piece could be placed on the board, create a big, long random number associated with that, like a 64-bit, 128-bit random number. And so I'll show an example of this in a bit. And the idea here is that our hash is going to take every single piece on the board, take the random number associated with all of those pieces for all the players on the board, and XOR them together. Well, how the hell is that going to work? Well, first of all, why do we use random numbers? Well, the reason we use random numbers is because if we have a large random number associated with every possible piece being on every possible location, that it's unlikely for that to cause hash collisions, right? Versus if I had actually, I'll show that in the slide. So XORing on those numbers creates a new number associated with a new state. So for example, if I have 5 pieces on the board, right? This is a black rook on square A1 and a white queen on square C4 or something like that. And so I XOR them all together. If these are, evenly distributed random numbers, then the XOR of all these is likely to be a number that is not associated with any other state, right? Now, there are far more chess states than we could possibly store in an integer. So yes, there will be states that cause hash collisions, right? That's just unavoidable. There's too many. There are more things than we have buckets to put them in. There will be hash collisions. But this strategy is way better than, say, assigning the value of 1 to the first thing, and then the value of 2 to the next thing, then the value of 3 to the next thing, because we've got all these zeros that we could be using for random entropy that we're not using. So big random numbers, it's less likely to cause collisions. So let's look at an example. Let's take an empty chessboard. We've got no pieces on the chessboard, so the Zobrist hash function is 0. Okay? 0 means empty board. Intuitive so far. Let's say I want to add a piece to the board. So I'm going to add a black pawn to b7. So I go to my big Zobrist table of random numbers. I look up, so for example, if white is 0 and black is 1, then this will be Z0 pawn, maybe a pawn is piece 0, so that might be 0. And then B7, that might be, you know, that's one of 64 possible locations. So let's say that's position number 10. And so this will be Z0010. That's going to be some big random number that's associated with that piece being on the board in that location. So in order to modify my hash function, I take the current hash, which was an empty board, and I XOR it with R4. And anything XOR 0 is itself, so what I have here now is the Zobrist hash for that particular board state of a game of chess. Okay? Now, let's say I want to remove that piece from the board. Then all I have to do is, well, putting a piece on or taking a piece off is the same operation. If I want to remove this piece, I XOR it with that value. Oh, I have another slide here. So just remember that XOR is reversible, etc. So we can remove a piece the same way that we apply a piece. It's just toggling on or off, which is what XOR does. So if I want to remove it, then I've got that same value associated with a black pawn being on B7. And so I XOR it with that. And look, the piece was there. Now I'm XORing it with the piece being there. And now the piece is not there. So we get back to that empty bit board, right? So let's do a little bit of a bigger example. Now I have 5 different pieces. So I have a white pawn on B6, a white pawn on C5, etc., etc. Each of these have random values associated with them. And so the Zobrist hash of this table, or this board state, is all of those XORed together. And even when it gets this complicated, if I want to, for example, remove that white pawn on C5, well, that had the value of R2, so I XOR that with the whole thing, and now there's 2 R2s in the XOR. Anything XOR itself and its transitive is 0, and so now I end up with that, and that's the board state. So it's this really cool function, and then we take that value, and let's say our hash table, we've allocated 128 megabytes. You take this value, which might be between 1 and several trillion or whatever, and then you modulus that with the size of your hash table, and you have your index to store this thing in the hash table. And then similarly, if I wanted to take this off the board, I could do that, and it would just be R6, XOR R6. It would become 0, and now that piece is no longer there. And so that is one of the more popular ways. There's one other way of hashing game states that I've never personally done, so I didn't include it. But in assignment 3, the thing that you are going to have to do is calculate and display the Zobrist hash of a particular state. Okay, so just create a big, and for Connect 4, it's way easier because it's just a board, and it's either a blank space, it's a yellow piece, or a red piece. So there's 3 possible integers. There's 42 possible places. You create that random thing whenever you... Oh, and here's another cool thing. You might think, okay, that's cool, but I got to calculate this hash every time I visit a state to look it up in the transposition table. That's a really slow thing. I'm going to have like 30 pieces on the board. That's 30 XOR operations, 30 lookups into this table. Here's the cool thing. Zobrist hash function